Thank you. And thank you to this morning's speakers for setting the stage. So I'd like to mention that a lot of this work and a lot else besides on galactic dynamos is covered in a living reviews of computational astrophysics that we have submitted and put up on archive. And we have not heard back from the referee yet. It's been a month or two, but if you have any comments and get them in to us before the referees reply, we would love to try to include them. So.
Do you have any message for the referee?
Well, we're waiting, but we understand that it's, 50 pages and it takes a while to go through something like that. So we will be patient. We have other things to do. So I think these slides have already been shown in some form, but there are two predominant dynamo mechanisms in galaxies. There's a small scale or turbulent dynamo that takes kinetic energy. Here's the kinetic energy spectrum, Kolmogorov, more or less, and turns it into a magnetic energy spectrum that peaks at a dissipation scale and then grows over time until it absorbs some fraction of the kinetic energy, typically a few percent before the kinetic energy at the dissipation scale starts to all be swallowed and you saturate. That sets the stage for the large-scale dynamo, which takes radial field, twists it and reconnects it, and it produces new flux that way, the so-called alpha-omega dynamo, where alpha is omega is a description of the differential rotation, and alpha is a description of the production of field. And I'll come back, I may come back briefly to alpha. Okay, so in a galaxy, in the diffuse ISM, as Christoph reviewed, one of the dominant drivers of turbulence is the supernovae. And so the question was raised, now many years ago, as to whether supernova-driven turbulence would drive a small-scale dynamo. And the answer appears to be yes. So this is already work we did in 2004. This was done with a second-order TVD code. Here's the magnetic energy over time, and there's an exponential growth phase followed by saturation at sort of almost 10% of the kinetic energy. This was a low-resolution model, 128 cubed, a higher resolution model at 256 cubed. Okay, so that was a first attempt to show an SSD in the ISM. However, it started 5 years or so ago, people started raising the question of, were we actually seeing dynamo action here, or was this just field tangling? So to address that question, we used the pencil code, thank you, Axel, to redo this model, but now with a higher order, more accurate code. And so this is what those models look like. You can now see that we're resolving a tremendous amount of field structure, even in the hot cavities, much less in the cold gas. And here's what the density looks like. So you can see that this thing indeed is a hot cavity. And we then asked, first of all, we implemented physical Laplacian resistivities and viscosity. So this is actually a strictly non-ideal MHD model. Then the question is, did we actually put in enough resistivity that we're doing more than the numerical resistivity and viscosity? And so the first attempt we made to check that was to just start with the resistivity and start it at 0, the blue line that's hidden under the green line here, go to 10 to the minus 5, which made no difference. Okay, so we're not resolving 10 to the minus 5. 10 to the minus 4, barely. And then 10 to the minus 3, we're certainly getting a difference. So that would argue that, yeah, somewhere between 10 to the minus 4 and 10 to the minus 3 is where we're starting to resolve. This was for half parsec, and then we did a resolution study at 1 parsec and 2 parsecs, and showed that the 10 to the minus 3 case, there was still so much numerical diffusion that we never got the dynamo going. Okay. However, when I gave this talk recently, Charles Gammy, who is somewhere in the audience, I hope, raised the question of, well, wait a moment. In a Kolmogorov cascade, it doesn't matter where your dissipation scale is. You're still going to get the same answer if everything's going well. So we went back and looked at one of our stratified box models and directly looked at where the dissipation scale is, which was a great idea. And lo and behold, here we are, 8 times 10 to the minus 4, and that's this line. There's the dissipation scale. 6 times 10 to the minus 3, more resistivity. We've shifted over, and 4 times 10 to the minus 2, we've shifted over again. So we really are resolving a Laplacian resistivity. We've done the same exercise for the viscosity, but not here, because we were holding the viscosity constant to vary the resistivity. Okay. Now that we have some idea that we're maybe doing a physics problem, or at least a math problem that approximates a physics problem, how does this behave? Well, because these were relatively small boxes, 256 parsecs cubed, we actually see quite a bit of intermittency when we run at a fraction of the Milky Way supernova rate. And as a result, we get intermittent behavior in the dynamo. However, what became very clear is that resolution matters tremendously because of the amount of numerical resistivity it introduces. This is a 4 parsec run. This is a gigayear. It took a full gigayear to reach saturation at 4 parsec resolution. At 2 parsec resolution, it was 200 megayears. At 1 parsec resolution, it was 50 megayears, maybe 30. And at 0.5 parsec resolution, we're down to just a few megayears. That was at 10 to the minus 4, which is probably still pretty much dominated by numerical. When we go to 10 to the minus 3, which we showed several ways now, is physical Laplacian resistivity, we're actually converging on a very fast growth time once you get a dynamo going. Once you have a region that's susceptible to a turbulent dynamo, it goes. And this has actually been shown, for example, by Reeder and Tessier, even in full galaxy models, although they went from like 3 gigayears to half a gigayear by going from 200 to 16 parsecs or something. And of course, Schober et al. Makes the argument that since the Reynolds number is proportional, Reynolds number to the 1/2 is proportional to the growth rate, that as long as you're dominated by numerical diffusivity, you should be seeing this sort of behavior. These were essentially Prandtl unity runs, although we've changed the Prandtl number, and I'll mention that later. As a result, if you go to full galaxy models, you get these long, slow, turbulent dynamos that can take, gigayears. That's a numerical effect. If you're doing galaxy formation, you need a model, as is now being developed by Tessier's group and others, that puts in the small scale dynamo because you can't resolve it. And so you have to start with a sub-equipartition, but pretty strong field as soon as your galaxy forms, because the accretion flow already is producing a small scale dynamo. And that's now been shown by Schober and Schleicher and so forth. So, caveat simulator. Let's compare back to those 2004 models. This is actually showing the capability of a higher order code. So here is the green one, the purple one is 256 cubed with a second order TDVD code. And the equivalent one is this red line. So look at how the magnetic energy just pops up in a few mega years. Same resolution, sixth order code, second order code. The same comparison is this khaki line versus the blue lines. Order matters if you're trying to do a dynamo because all the action is in the smooth flow. You have to jump through all sorts of hoops in order to resolve your shocks and maintain them stable in a sixth order code. We have an entire paper about that didn't even include all the hoops we ended up using. But once you do it, it's well worth it. Okay. Is this field tangling? Okay, we did a model where we forced tangling by pushing the magnetic Reynolds number down so far that there couldn't be a dynamo. And this is what the power spectrum looks like. So the kinetic power spectrum is concentrated at the forcing scale. And the magnetic power spectrum drops like a stone below the forcing scale. Compared to a dynamo, kinetic energy, this is now an idealized periodic box dynamo with a uniform forcing field. Again, the kinetic energy is concentrated at the forcing scale, but you get plenty of magnetic power. First of all, it grows by many orders of magnitude, which you don't get from tangling, which just grows linearly for a short amount of time, from 1 to 7. Okay, fine, but it's still 10 to the minus 22. Whereas here we're going, boom, 10 to the minus 6. Okay. But anyway, you also get lots of power below the forcing scale and above the forcing scale. If we look at our supernova-driven boxes, here's the effective forcing scale of supernova-driven turbulence, somewhere around 100 parsecs, and there's plenty of power below. This is not tangling. A couple of years ago, Christoph Federath argued using isothermal models that there was a strong dependence. Okay, it was several years ago, sorry. That there was a strong dependence of SSD growth rate on the Mach number using either solenoidal or compressible flow. So we went looking for that as well. What we found, these are the growth rate averaged over regions of different phase and regions of low growth, medium growth, or high growth. So you can see that the fastest regions of high growth are growing very fast. This is also multiple resolutions. The red is picking out the highest resolution model. And what we found was that there was an extremely good correlation with the entropy. Okay, so the entropy of a region tells you, reading off a scale, how strong your growth rate is. The Mach number, not so much. This is Mach 0.1, this is 1, this is several. There was no tight correlation between the Mach number and the growth rate. There is, well, it really just depends on the details. The same was true for the magnetic Reynolds number. Now, this is in a non-isothermal, non-uniformly driven model. My current hypothesis, speculation, is that it's the lack of an isothermal equation of state that's driving this, because you can generate vorticity from shocks in an adiabatic equation of state with cooling that you can't generate in an isothermal equation of state. This is, however, speculation. It has not been tested yet. Maybe someday someone will do it. What about the magnetic Prandtl number, which has been argued to be extremely important? So we varied over some range of 50, the magnetic Prandtl number. And we did it 2 different ways, by varying the resistivity and by varying the viscosity. And varying the viscosity didn't change much. Varying the resistivity, the magnetic Reynolds number, absolutely changed the behavior. Skip this khaki line, but you still can see that there is a substantial difference. Thank you. Keep moving. To be discussed further. Okay, transition from the turbulent small-scale dynamo to the large-scale dynamo. So, what happens when we include differential shear and in order to capture a galaxy, also stratification? So these are now kiloparsec by 400 parsec by 3 kiloparsec models of the galactic plane and above. This is the magnetic energy growing over time rather slowly after the initial jump. And this is a 1 parsec resolution model. This is the azimuthal magnetic field. So you can see the shear, and you can see that there's starting to be structure growing in it. If we look at the growth of energy, okay, these models are low resolution models. L2, the blue line, is probably the fiducial one. Delta X is 4 parsecs. So you get a long, slow, small scale dynamo, and then a transition to large scale, which hasn't quite saturated at 2 gigayears. We have a high resolution model running. It's hella expensive, but now you can see what small scale dynamo does. And again, we haven't quite reached saturation, but we're getting there. And we actually tested what happens if you take out the large scale field, so that we can look at the pure SSD. Without shear, there's actually less magnetic energy than there is with shear. The SSD is actually, if you compare apples to apples, stealing energy from the large scale dynamo. Are we getting a large scale field? Yes, yes we are. Here's the magnetic energy power spectrum over time. So at early times, you see that classic Kazantsev small scale dynamo spectrum. Then as the large scale dynamo takes hold over a gig year, you see the large scale growth. You can also watch the large scale field component as it grows to exceed all the other smaller scale fields. However, if you add all these fields together, the large scale field is only about 20% of the total, agreeing with observations. Brand new result, which is why it's not in the text on the slide. Fred Dent only derived it like last week. Okay, I've got a 3-minute mark, so keep moving. If we look at the horizontally averaged field, this is the normalized version, so you can see what's going on when it's low strength. This is the low resolution model, so it takes a while to grow in strength. But you can see that there are field reversals and then a uniform horizontal azimuthal field at late times. This now runs out to 5.5 gigayears at 4 parsec resolution. Let's look at the helicity. So that same model is here, and you can see that the helicity is actually controlling the field direction. So you had a reversal in helicity, and that controlled the reversal in field direction. Notice that the magnetic helicity grows with the field, while the kinetic helicity is pretty much constant over time. If you go look at the high resolution model, we only have half a gigayear. This is my last substantive slide. And so it's really just this piece, but this is what the kinetic and magnetic helicities are doing in the high resolution model. You can see that there's opposite sign helicity crossing the midplane, and what you get is little ejections of opposite sign helicity going out, and then the big regions are actually more associated with inflow. And since I now have the deep purple sign, I'd better go to conclusions and say that the turbulent small-scale dynamo is easily driven by supernovae. Entropy is what controls it. Magnetic energy typically saturates maybe 5% of the kinetic energy in like 1 or a few megayears, not gigayears. and we can derive some sort of critical resistivity. It appears to be not so sensitive to magnetic Prandtl number, although we certainly want to explore that over a greater range and hope to pursue runs of that nature if you're sitting on an InSight tack. And we don't need an imposed field for exponential growth. We started just with random values. Kazantsev scaling is seen. We see the LSD, the SSD and the LSD compete for the same pool of kinetic energy. So when you have an SSD, the LSD grows a touch slower. We have magnetic helicity growth and ejection. Thank you very much.
Thanks, Mordecai, for a very interesting talk. We have questions, please. CEO, first one. And please all line up.
James?
Very interesting.
It may
Yeah,
not be on. Check for a red light on it. There's a button right
there. We go. Beautiful. I had quite a few questions, but I'll just ask my last one, I think. So can you go back to your helicity slide?
Of course.
Next one.
Yep.
So what I'm seeing in the bottom right corner is the current helicity, not the magnetic helicity. So is this current helicity or is this magnetic helicity?
Current helicity. Sorry.
Oh, this is current helicity.
Yeah.
Which is relevant to quenching.
What's that?
Which is relevant to the quenching, I would
Relevant
say.
to the quenching. So you're arguing that the sign of the current helicity is changing the sign of the large-scale magnetic field, is that correct?
I believe so, yes. I mean, what I'm pointing at is this structure compared to that structure.
Okay, thanks.
Yeah.
CEO?
So the fluctuation magnetic energy I found is like you said it's I forgot the number, it's smaller than the turbulent energy, right?
If the fluctuation dynamo produces magnetic energy smaller than turbulent, yes.
Yeah, so in terms of the correlation length of turbulent magnetic field, what implication we get from simulations is whether it's consistent with like a rotation measure observation?
The small scale dynamo will not produce correlation lengths consistent with rotation measure observations. You need the large scale dynamo to do that.
I mean, is it like a 100 parsec or smaller?
The small scale dynamo correlation length, because of the Kazantsev spectrum, is going to be way down near the dissipation scale. It's going to be smaller than the 14 scale of around 100 parsecs.
So you say a simulation get very small correlation length of the turbulent magnetic field in asset?
So let's see what we can do here. Whoops. The initial correlation, come on, there we go. Okay, so right off the bat, this is what it looks like at small scale, for a small scale dynamo. It's just a mess. It's not until this grows big enough for the large scale dynamo to take hold that you start getting significant fractions of a kiloparsec structure.
Yeah, but it's not, maybe
We're going to have a discussion right after this. We can continue.
Ethan.
You're going to discuss right away.
I know, so this is cheating.
Brief question.
But I wanted to clarify something.
Please.
So when you were showing the current helicity and the kinetic helicity,
Yes.
you said they were the same sign and they both drove the large-scale dynamo.
I'm not sure I said that, but I think maybe it's.
That's what I heard.
Yeah, okay. Maybe I'm willing to defend
Mutually
that.
supporting.
Yeah.
Okay, but
They quench each other.
But the alpha if you calculate the alpha effect in a dynamo, they come in with opposite sign. So if they have the same sign, they are not acting in the same way.
Yes,
Sorry, I got the sign wrong. You're absolutely right.
So which is it?
It's what you said.
Which one? So is the sign in the plot wrong? Is the question.
What's that? Okay, so the signs here are correct, in the plot are correct. However,
so the statement was incorrect only.
the statement was incorrect.
Yeah.
The statement was
the
incorrect.
text that I wrote late last night was incorrect.
So they
Sorry
do
about
not
that.
both support the dynamo.
Yeah.
One of them supports the dynamo and one of them quenches.
So what I think we're arguing is that because we have opposite signs in both hemispheres, that we're actually transporting helicity in order to avoid saturation.
Getting complicated. Next
Or
one,
vice
please.
versa, but okay, thank you.
We should discuss it, of course. Next question, please.
Hi, Mordecai.
Hi.
Thanks.
You can pull it out.
Sorry?
You can pull the mic out.
Yeah.
No, just the mic itself. There you go.
I'm actually
Okay.
happy to see that, that's already the second talk that considers numerical dissipation and like all the things associated with that. So I have a numerical question, which is for the 6th order plot that you showed. The growth rate seems that the dynamo or like the field actually decays again. Have you run that for longer? Like what happens in the long, like way earlier?
Yeah. There.
Yes. So the red line seems to decay again. Like
Yeah. Well, the problem is that these small supernova in a box models tend to move into a all hot plus all cold phase, which is kind of physically unrealistic because you don't have any place to vent your heat, and you're just relying on your cooling to do that, and it goes wonky. So it's not a great long-term model to just run and run and run.
And then, like on the next slide, the physical question would be like the difference between like dynamo and tangling. Like, what exactly do you mean for the small-scale dynamo? Like, are like on the second, on the left-hand side, the bottom 2 plots, are they the same resolution, or why there is no power on the small scales?
Okay. So what we're doing here is just varying the strength of the resistivity. So here we've suppressed the small-scale dynamo. Here we haven't. These are both uniformly driven periodic boxes. This was just basically an experiment to understand what the spectral characteristics of tangling versus a dynamo. This is work that's associated with other work that Nishan Singh had done.
So what kills the kinetic energy in the bottom plot?
That's a fair question.
I mean, you're saying there's no dynamo. That's why it's
yeah. Well,
not going
he's
higher.
asking
It's an
why
interesting
kinetic energy
thing. We need to
also,
check this.
I don't actually know the answer to that.
Good.
It's a fair question.
Next question to Betsy, please.
Oh, okay. Very nice talk, very nice results. But yeah, I have a question in the same line somehow to Ethan's. So you do identify an alpha effect, and you claim that directly from the simulations you do have this smooth transition from small scale to large scale dynamo, right? And then what is the driving source of the large scale? Is the large scale shear motions? Are you including rotation or not?
Yes. Yes, okay, we're including rotation, and indeed we're spinning it rather faster than the Milky Way in order for the large-scale dynamo not to take forever. It's both rotation and we have an appropriate local shear.
And so you have both alpha and omega effects
exactly.
At some sense.
Yes.
Christoph? Thank you.
Yes, I think I'm interested a bit more in comparing the different numerical methods and resolutions and the effects of that. So one of the plots you had was comparing, I think, Axel's higher order scheme with something else, and I don't know what that something else was.
It was the Balsara second order TVD method from 2004.
And quantitatively,
okay, so we're comparing this model, which is second order TVD, to this model, which was 6th order pencil code.
So
or
you're saying
similarly,
there's a huge difference in the growth
this one
rate.
versus that one. Correct.
And you're attributing this
to order.
Solely to the order.
Yes.
Okay. Good to discuss a bit more.
Mm-hmm. Is it actually the resolved Reynolds number that's changing? So, I mean, that could be explaining
so
the growth rate
effectively,
completely.
yes. So what's happening is that in this case, the numerical Reynolds number is being determined by the second order dissipation, numerical dissipation here. Here, we're basically resolving down smaller wave numbers and thus have effectively lower numerical dissipation.
Can I ask the last question? Or?
Yes, please go ahead.
I was just looking at your ISM box simulation visualizations that look very beautiful. Maybe you could bring them up. I see all these breathing modes in the disk.
Oh, yeah.
So are those desirable? Normally, if I'm doing supernova-driven turbulence in a disk, these breathing modes only come about for particular distribution functions of where I put the supernova.
Interesting. So we already saw those modes in Hill et al. And frankly, Don Cox had already predicted that you would get that sort of behavior back like in the 90s. And we were able to reproduce the frequency in Hill et al. 2012.
Is this a stationary simulation with these breathing modes?
More or less. I mean, as stationary as you can get while losing mass out the top of the box. Yeah. We didn't add mass in the midplane to make up for losing mass out the top, but we're still running for gigayears and not losing all our gas. So it's close.
Okay.
Yeah, you do see we do have a boundary condition that if you're infalling, just reproduces the boundary. So you get those stripes, which isn't perfect. And we're kind of actually niggling it, fixing that. But the midplane isn't going to be dramatically modified by that.
Thank you. If you could go to the sketch on your second page or something.
Uh-oh.
There was an interesting...
Look, this one.
Yes, this one, the previous Kazantsev, the other one. Yes. So the Kazantsev spectrum actually stays shape invariant. Here you have the peak moving. That's actually not really happening. So
blame Rincon. I stole the cartoon from him.
It's not yours.
Sorry.
Tell him. Thank you very much for a very interesting talk.
You're welcome.